Good evening. Am I audible?
Yes, ma'am.
Okay. So the screen is visible, right?
Yes, ma'am.
Okay, great. So again, welcome to Fundamentals of my Wireless Communication tutorial. I'm Rubina Afreen, Prime Minister Research Fellow from IIT Hyderabad. So, in case you are not able to join this lecture, this video will be uploaded on YouTube, and maybe we will shift to Zoom or something else from the next week. Discussion is going on for the same. So, this week we will start with. Last week we have been discussing about large scale propagation model, and today we will discuss about small scale propagation model. So, as we discussed previous week, there is this two types of models we are considering. Okay, there is large scale propagation model and there is small scale propagation model. In the large scale propagation model, we discuss path loss and shadowing. This was covered in previous week lecture. Then in small scale model, we will see multipath, then frequency flat fading, and envelope distribution. So what happens is that when distance between transmitter and receiver is very large, if d is large, then we consider large scale propagation model. And if d is in the order of wavelength like 10 to 100 times, then we will be considering small scale model. So as we said, distance is very less in small scale model, like some tens of wavelength. So here signal will fluctuate. One assumption that we carry in small scale model is that the mobile station is moving. So when mobile station is moving, we will consider the Doppler effect. So suppose that we have any wave incoming and we have the mobile station that is moving with the velocity v. So for Doppler, we will always consider the angle between the incoming wave and the velocity of the mobile station. Now suppose this will not always go in a straight path. Now suppose the mobile station is moving in this way. We have some antenna. So incoming wave is in this part. So what will be the angle? Angle will be this. Now whenever we consider the transmitter and receiver model, so we have some antenna height, but then here we will be ignoring the antenna height. We will be taking two-ray model. So because of, as we said, that this is moving, mobile station is moving, so Doppler shift will be increased. Doppler shift we will be writing this. This is in hertz. FM is the maximum Doppler shift. This is equal to V by C. So as we explained in the previous tutorial, signal is coming from all direction. So here we are considering the nth incoming signal. So this nth incoming signal is depending on cos of theta. Now moving on. This thing we have discussed in the previous class. The transmitted band pass signal we will consider as S equals to real part of this is the received signal RT. RT is the real part of S tilde t e to the power j 2 pi f c t. Right. This I explained in the previous class. This is the transmitted signal, right? So this is the complex envelope, and if we say at the received side, what will happen is that the signal will be scaled by some amplitude. So this is the scaling effect. Then as we consider that the mobile station is moving, so there will be some Doppler shift here. And then since we are considering reflection from n path, so there will be a t minus tau 1 term. This is the delay introduced. So t will be replaced by t minus tau n here also. Now we have seen that the phase difference we have taken as phi n. So the whole term be replaced by phi n. And then received signal we have written as real part of this term into e to the power j 2 pi f c t. So received signal we can write as real part of r tilde t e to the power j 2 pi f c t. Hello Ram, welcome. So we will carry on from here. So now at the receiver, what is happening is that different signals are moving through different delays, and different Doppler shifts are included. So the received signal we can write in this form. Now what we have done is that from here, this r tilde t we can write as summation of n equal to 1 to n c n e to the power j phi n into s tilde of t minus tau n. So this term cn into e to the power j phi n we can write as the channel for the nth path. This channel is a function of time because this phi is varying as a function of time. So from there we derive the channel. So in the past lecture, previous weeks, we have written the received signal as a it's like the first signal delayed by tau 1 multiplied by the channel coefficient from the first path. So like that, here we see that multiple paths are introduced. Now see this. Can we write it as ht convolved with s tilde of t? Here h of t comma tau is summation n equal to 1 to n ht comma tau n into delta of tau minus tau n. This we can write as h and t, that is the channel for the nth path, which is a function of time. So now what we are saying is that if this is the delay axis tau, the magnitude of the h n t will vary with each delay, right? So to describe this, we take a new dimension delay, and then we have this tau 1 tau 2, say any general tau n tau n. The first channel response is delayed by tau 1. You can see here delta of t minus tau 1. Now the second one, suppose it is at tau 2, similarly like this. So this can be considered as the filter taps. We can say that at the transmitter we have a signal st which is generated at the time t minus tau 1 and is multiplied by h1 of t. Then it is added to another signal st that is generated as t minus tau 2, and then it is multiplied by h2t and so on. So can we conveniently say that the received signal has multipath interference? Because see, this signal multiplied by this will be added to the signal coming on from here. These and all will be added from the signals coming from the nth path. So essentially what we are saying is, suppose at the transmitter you are transmitting the signal like this, anything. This is T1, T2, T3, T4, like that. Now each of these will be multiplied by some h of t and delayed by some tau and then added. So what I essentially mean is that suppose the first signal is there, it is delayed by some tau 1 and multiplied by some h1t. So suppose this goes like this. Now we have the second signal which is added, matlab superimposed on it. This has some other delay and some other h. Likewise we have some another nth signal which has delay of tau n, and then it is going on like this. Now you see what happens at the receiver. The signal is getting interfered by the other signals. So at the output we don't know what kind of output it would be. Now it would be totally random. Anything we cannot predict. So this will be some very arbitrary sequence. This is RT. And this is what summation of H and S of T minus tau. So this is the total multipath model. From here some assumptions we will take and then we will go to flat varying. So now suppose that we have a transmitter, we have a receiver. Signals will be going after multiple reflections from the transmitter to the receiver, right? So suppose the signal is taking time tau 1, the signal is taking tau 2, tau 3, likewise another signal is taking time tau n. Now one important assumption that we are making here is that we are saying this tau 1 is approximately equal to tau 2, likewise this is approximately equal to tau n. Consider this as tau n. So what we are saying is that any path the signal is coming from transmitter to receiver, any from anywhere it is getting reflected, that total time is same. So can we say that the transmitter and receiver are located on the two focus of the ellipse. So what happens is that any reflection happens, the total delay would be the same, right? So now since every delay we have assumed is to be same, so this would be negligible, right? Now what will happen if this is the delay axis? There is one common delay tau and all the channel coefficients are here only. Likewise at the receiver, suppose we have this as the transmitted signal, okay? Now delay is very minimal, only scaling is there. This can be easily decoded at the receiver. So essentially what we have done is that we have this we have approximated as now we can take it as now since there is delay is common, we can take it as ht. So now what I mean to say is that all the transmitted signals are delayed by one common delay and it is multiplied by ht and we are getting the received signal. So take it now. If we take its Fourier transform along delay domain, so we can say that this is h of t and there is some frequency nu. So this will be time varying, but we are taking frequency Fourier transform along the delay axis. So this would be integration from 0 to tau max. This will come as ht into e to the power minus g 2 pi mu. Okay. From here we see that mod of ht, or maybe write it as ht comma new, because the mod of this term will be 1. So from here we can see that the h in frequency domain is not dependent on frequency. So suppose we have this time axis, h is varying in time, right? Here we consider the frequency axis. So what we are saying is that along this axis h is constant, but at the same time h is varying along time axis. So this thing will always be same. This will always be same, but it will be varying in the time axis. Like suppose this is mu1 to mu2, so this will be constant. This length will be constant, but it will vary in the time axis. This fluctuation is in the time axis. So this type of fading is called frequency flat fading. Why frequency flat fading? Because it is flat in frequency. It varies in time, but it is flat in frequency. Frequency flat fading. But I hope that is clear. Now one simple concept that I will discuss is envelope distribution. Till that we write as summation n equal to 1 to n cn e to the power j phi n, which is a function of time, and then we have s of minus tau n. So suppose if s tilde t is 1, then can we write this rt as ht? So ht we have as n equal to 1 to n cn e to the power j phi n. We expand this, and then we can write it as summation over n to 1 to n cn cos of phi n t plus summation n equal to 1 to n cn sin of phi n t. This we can write as in phase term plus g times of quadrature term. Now we see that these in phase component and quadrature component are function of t. This phi n is a function of t. This phi n is 2 pi fm tau something. So here these tau we are taking as same, constant, but frequency, this phase difference we are not taking as constant. We are saying that this one assumption we are taking is that even for a very small change in tau n, there is a large change in phase. That means if tau n is of the order of 1 nanosecond, even it gives a phase change of 2 pi. So phase change we are assuming as random. So phi n we are saying is uniform random variable. We take phi n from 0 to 2 pi. So see, we have HITS summation Cn cos of phi n t. The Cn is also random, but typically we are considering the Cn as suppose 1. Now this HIT and HQT, these are sum of random variables. So suppose if n is fairly large, can we say by central limit theorem that HIT and HQT are Gaussian? Correct. So now the HT we have is HIT plus J times of HQT. So what is this? Sum of complex Gaussian random variable. So this is complex Gaussian. Right now, this H is modeled as random variable. At the output of the receiver, what happens is y equals to hx plus n. So now, initially we used to say that uh, when there was no channel, AWGN channel was there. So the signal was somewhat corrupted with noise. So if we had transmitted this, if AWGN was there, so we will get some output like this. There will be some fluctuations, but essentially we will know the shape of the signal. But now here it is multiplied by one random variable. The magnitude is random. So now in case of fading, we will have any random shape now. Not even this. It will go as this. Anything can happen. So this is for fading. And this is AWG. Now this envelope of ST. This is what Rayleigh distributed. And alpha square T, that gives the power profile. This gives the signal strength. This is given as exponential distribution. So maybe you just write the PDFs, do this homework because this is very important. So you try to find out the envelope and the signal strength. It should come as Rayleigh and exponential. We will move on. I am not going to describe this thing, but maybe if you have any doubt, you can mail me or ask me anywhere. So here we have seen that this envelope is Rayleigh distributed. Similarly, we consider other type of distributions also, like Rayleigh distribution or Nakagami distribution. So very briefly I will describe and then we will move on. So in case of Rayleigh fading, what happens is that the signals are coming from all sides. Like if this is transmitter and this is receiver, signals are coming reflected from everywhere. There will be multi paths, but every there is no any signal that has dominant strength. So this is for relay fading channel. In Rician fading, there is one LOS component that has most energy. So in Rician fading channel, there is one specular line of sight element. So here in relay fading, we consider that the channel is given as HIT plus JHQT, where both of these are Gaussian random variables with zero mean. In Rician, HIT and HQT have non-zero mean. Suppose say MIT and MQT. So in this case, even now I will request you to just do it, like compute the envelope of in case of Rician fading. What you have to do is that here in this case you have zero mean random variables. In Rician case, you just take some non-random, uh, non-zero mean Gaussian random variables, and then you calculate the envelope of this distribution. So the PDF of distribution is x upon b naught exponential I naught of xs upon b naught. Here s square is mi square t plus mq square t. I naught, you know, is the modified Bessel function of first kind. Rice factor we define as k is equal to s square upon 2b naught. Here in this case, if k is infinity, uh, if k is 0, this is equal to Rayleigh fading. If k is infinity, then this is no fading case. So what happens in Rician is that, suppose if k is infinity, this will be very much peak with very less spreading. If k is 0, it is almost Rayleigh fading. So this is for k equal to 0 and k equal to infinity. So from here we can see that as k increases, spread will decrease. So for Rician, in case of exams also, you don't need to remember this probability distribution. Just you remember this figure, and you remember that when k is infinity, it is no fading case, and when k is 0, it is really fading. So now suppose I'm taking two more. This is k1, and this is k2. What do you think? Is k1 greater than k2 or k2 greater than k1? Tell me. Are you there, Dishan?
Yes, ma'am.
You understanding?
In what sense, ma'am? K1 is greater than. I'm not sure.
Sorry.
Like, what are you asking? Like, K1 is greater than K2 means.
See, this is Rician fading channels envelope, right?
Hmm, hmm,
So what I'm saying is that if k equal to 0, we have the Rayleigh fading pattern. And if k is infinity, that will be no fading. Now
mm,
I have taken two plots. You see k1 and k2.
okay.
Okay, this green curve is for k1 rise factor,
Mm.
and this pink curve is for k2 rise factor. Now, if I ask whether k1 is greater or k2 is greater, this is A, this is B. What do you think is true?
Like fading in case of K1 is greater, or fading in case of K2 is greater? You are asking that, or?
No, K is rise factor.
Mm.
Okay, rise factor will decide the spread of the curve.
Okay. So
Like,
rise factor is more in K1. K1 is greater than K2.
no, rise factor. See, K equal to 0 is for Rayleigh case, and K equal to
Mm.
infinity is for when there is no fading. Right.
Mm.
Now you see, spread is more in K equal to 0 or K equal to infinity. When there is no fading, then it will be more like an impulse, right?
Yes, ma'am.
Correct now.
Mm.
So you see this green curve, and you see this pink curve. Which of these has less fading, less spread?
Less spread in K2.
K2, right? Less
Yes, ma'am.
variance. So here K2 should be greater than K1 or K1 should be greater than K2. See this, as K is increasing, the spread will decrease. Okay, I'll explain it again. Okay.
Yes, ma'am.
Hmm. So when there is Rician fading channel, we have a dominant LOS component. That means that out of all the signals that are coming, there is one signal that is specifically higher power. How do we model Rician fading channel? This HI and HQ term that initially we were considering as Gaussian random variable with zero mean, now we are considering them as non-zero mean. When you compute the envelope of this HT, the PDF of that alpha T, I should mention it here, alpha T is envelope of HT. So PDF of alpha T is Rician in this case when the mean is non-zero. So this is the PDF of the Rician function. Here S square is the squared sum mi squared t plus mq squared t. Rice factor, this is very important for Ricci distribution. Rice factor k is defined as s square upon 2b naught. Right. So here we say that if k is 0, it is Rayleigh fading case. And if k is infinity, it is no fading case. So as k grows from 0 to infinity, this curve will narrow down. So initially, if this is the case for k equal to 0, for this case,
Yeah, got it, ma'am. K2 is greater. Like
yeah,
if K is increasing, the spread is decreasing. Yeah.
correct. So in this case, K3 will be greater than K2 will be greater than K1. If this is for K3, this is for K2, this is for K1. And that is clear now. So now till now we have seen Rayleigh fading channel and Rician fading channel. So one more we will see Nakagami. This Nakagami fading is will explain both Rayleigh and Ricci. From the PDF Nakagami, we can see that it is a very general case of fading, which will include both relay and Rician type of fading. So I'm not going into the details because this is not very much used. In whole communication system, relay fading channel are sufficient. So these and all I'm just explaining so that you can do the assignments and exams. I will write down the PDF. Omega P is the envelope power, that is signal strength. So again, there is no need to remember this PDF. Just remember that when M is 1, it gives Rayleigh fading channel. You can see from the PDF also, put M equal to 1. And then if M is half, it is Gaussian, one side Gaussian. And if M is infinity, then this is no fading. So here also what is happening is that with the value of M, increase in the value of M, the spread will decrease. Is this clear till now?
Yes, sir.
Okay, then one question we will see here. Are you able to see this question clearly?
Yes, sir.
Okay, 4 plots are there, A, B, C and D. It is asking which of the following PDF has highest value of M. What do you think it is?
For C,
Please repeat.
C,
C. Correct. You can see as the value of M is increasing, spread is decreasing. Okay, one thing if I may ask, what is the value of M for the plot A? Can you tell? For Rician, for Nakagami distribution, if M is 1, it gives Rayleigh fading. If M is half, it gives one-sided Gaussian.
then for A it's 1/2, like half.
Correct. For B,
For B it's 1. It's
1.
Rayleigh.
Rayleigh fading. Very nice. Okay, so now that is my cue that this concept is clear now. One more important point is that there is some relation between Rician and Nakagami factor. This relation is given by K is square root of M square minus M divided by M minus square root of M square minus M, where M is greater than 1. or more simply, m is k plus 1 whole square divided by 2k plus 1. So in Nakagami distribution, only these two concepts are important. This concept and this one. These will solve mostly your questions because nobody asks question from the probability distribution function. So one more question we will see here. The formula is m is k plus 1 whole square divided by 2k plus 1. Now k factor is given as 1. Now can you tell the parameter m for Nakagami distribution? Can you calculate immediately?
4 by 3.
Correct. So k is 1. So m is 2 square by 3, that is 4 by 3. That will come as 1.33. So answer is D here. So this is all about feeding channels. We saw relay feeding channel, regime feeding channel, and Nakagami distribution. Now we will come to band pass signal correlation. So what happens is that at the receiver, the signal is corrupted by this channel coefficients as well as noise. So noise factor here we don't consider. We just considering the fading channels. So suppose as we saw previously also, I'll describe from here. Whatever the signal is, the signal after fading is very different, right? So suppose at the receiver we are receiving something like this. Now we would like to know the signal correlation, how much of the signal is correlated. This is very extensive maths, but I will just try to explain as much as I can. So at any point if you have any doubt, you just ask. RT we have as real part of HT, e to the power j 2 pi FCT. HT we know as HI plus J HQT. So we just write it as HIT plus JHQT. Now e to the power j 2 pi FCT we can write as cos 2 pi FCT and sin 2 pi FCT. So overall this will come as HIT cos 2 pi FCT minus HQT sin 2 pi FCT. Okay. What is the formula for correlation? If I are of delta t, this would be expectation of RT into R of t plus delta t. Right. So now we will put the values. We will write it as omega ct minus hqt sin of omega ct then it is hi t plus delta t cos of omega c t plus delta t minus hq t plus delta t into sine of omega c into t plus delta t. Now all we do is to multiply. So now we can write it as expectation of this term and this term will multiply first. So this will come as hit into hit plus delta t cos omega ct into cos of omega c t plus delta t, right? Then plus hqt plus delta t sin omega ct sin omega c t plus delta t. Now the minus terms hit hq t plus delta t cos of omega ct sin of omega c t plus delta t minus hqt hi t plus delta t into sine of omega c t into cos of omega c t plus delta t. Now we know the basic trigonometry formula. 2 cos a cos b is cos a plus b plus cos a minus b. 2 sin a sin b is cos a minus b minus cos a plus b. So we will use the trigonometric formulas here. And change the pen color. This is expectation of hit hi t plus delta t into omega c 2t plus delta t plus half cos omega c delta t. Okay, then next term would be hqt plus delta t half of cos omega c delta t minus half cos of omega c 2t plus delta t. Now remaining two terms hit hq t plus delta t sine of omega c 2t plus delta t of omega c delta t. Then the last term would be hit t plus delta t hq t into half sin omega c 2t plus delta t minus half sin omega c delta t. Now the next step we will do is to separate these terms. Cos omega c delta t, then cos omega c 2t plus delta t these two terms will be grouped as one. These two terms you group, then these two terms, and lastly these two terms. And after that, see, this is correlation. So here one assumption that we are making is that the process is white sense stationary. What happens in white sense stationary process is that the autocorrelation is a function of delta t only. So r phi r delta t will be a function of delta t only. So the t term would be 0. So the coefficient of this term would be 0 and the coefficient of this term would be 0. So I will just segregate the two terms. This will come as half cos 2t plus delta t hq t plus delta t minus expectation of hq t plus delta t. So this is one term that is dependent upon t. The other term is minus half sine omega c 2t plus delta t into expectation of hit hq t plus delta t plus expectation of hqt hit plus delta t. And then two more terms are there. That is, one is half of cos omega c delta t into some coefficient and minus half of sine of omega c delta t into some coefficient. So currently I'm not writing all of that, but the gist is that since it is just a function of delta t, all the terms that are function of t, that should be 0. From here we will get this coefficient equal to 0 and this coefficient equal to 0. So I will write it down here. Expectation of hit hqt plus mistakenly wrote as hq, here it is hit into hit plus delta t. This is equal to expectation of hq t plus delta t, and the other term is expectation of hq t plus delta t. This is equal to minus of hqt hit plus delta t. Now we take both of these. This is suppose 1 and 2, and we put them in the equation 3 and 4. Now we put them in this equation. So phi r delta t, in phi r delta t, these two terms would be 0 and the remaining would be these two terms. So just calculate it once. This will be coming as phi r delta t is equal to half cos omega c delta t into 2 into expectation of hit plus delta t, then minus half sine of omega c delta t into 2 into e of hit hq t plus delta t. From here this 2 will cancel out, and this term, this is autocorrelation of hi with hi delta t. This term into cos of omega c delta t minus delta phi of, it's always you write the term which has delta t, I mean t plus delta t term as the first. So this would be hq hi t, I mean delta t, into sine of omega c delta t, right? And when you take autocorrelation of h, it comes as phi of hi delta t plus phi of hq delta t. This thing just solve once and drop me an email if there is some issue. So we will be using this result into this one. We have phi r delta t is real part of phi hh delta t e to the power j to pi f ct, right? And hi we know as summation of n c n cos of phi n. Here phi n we are taking as uniform from 0 to 2 pi. So when you calculate phi of hi delta t, this is expectation of this term. This is a function of t. So this will come as m equals to 1 to m equals to 1 to m cn cos of phi n t cos of phi n t plus delta t. So I'm not going into much detail, but this will come as okay. So after this, what you have to do is that you take two cases. First, n is equal to m, and the second case would be n is not equal to m. So when n is not equal to m, this that case would count as 0, and the other case in which n is equal to m, that case you have to calculate. So finally, it would be something like n equal to 1 to m cn square half of cos of phi n t plus phi n of t plus delta t plus cos of phi n t. What we have done is that we have just taken n equal to m case and proceeded with it. So here it would be t plus t is 2t plus delta t. When it will be integrated, it will go as 0. Here it is phi n delta t, and phi n delta t is 2 pi if dn of delta t. So all in all, this term would equal to summation of n equal to 1 to n expectation of cn square into half of expectation of cos 2 pi f max cos theta and delta t, including the Doppler effect. This is equal to total power. So this summation n equal to 1 to n cn square is total transmit power. So expectation of Cn square would be gamma p upon n, and we know that p of theta n is 1 upon 2 pi. Finally, the expression that we would obtain is this equal to gamma p by 2 expectation in terms of theta cos of 2 pi f max cos theta into delta t, and phi of hq hi delta t. This we will get as, here cos will be removed by sine, 2 pi f max cos theta delta t. Now you just have to integrate to find the value of the correlation. And since this is even function, we can write it as, and p theta is 1 by 2 pi, so we can write it as 1 upon 2 pi into 2, 0 to pi, and then cos of 2 pi f max delta theta cos theta d theta. Now because of this cos theta, this will vary from minus to plus 1, so we can replace this cos theta with sin theta as well. So we will write it as 0 to 2, 0 to pi cos of 2 pi f max delta t sin theta d theta. This is the Bessel function of first order, so this will be 2 pi f max delta t. If we go to phi of hq hi delta t, this will be omega p by 2 into 1 by 2 pi minus pi to pi sin of 2 pi f max delta t cos theta d theta. So since sine function is odd function, the whole integration will go to 0. Now we have IHH of delta t is IHI of delta t. So what will we say for correlation? Suppose this is phi error of delta t. Since Bessel function is there, the signal energy will be decaying. So the plot would be like that. This axis is time delay. So at the time when the signal will reach the 90% of the maximum power, that is called as coherence time. Now we will see why coherence time is very important. Why are we studying all this? Coherence time we define as the separation of time for which the signals are correlated. That is why we consider the 90% of maximum power, so that signal is correlated in that time. So two formulas are there that you have to remember. First is TC is 0.423 divided by FM. What is FM? Can you tell?
It's V by C into FM. FC.
FM is V by C, maximum Doppler shift.
V by
Great.
C into FC, I guess. Because FD is equal to FM into cos theta n.
Correct. Yeah, okay, okay. FM would be V by C into FC. So FM is maximum Doppler shift. And another formula of TC is 9 upon 16 FM. So all the problems related to your coherence time are based on these two formulas. So it's very important that you remember. Just remember these two formulas of coherence time. This one is the stricter formula, and this is a bit relaxed. Okay. Now what is the significance of FM? Let's suppose so this kind of fading is slow fading, like, and then this kind of fading is fast fading. So normally what we say is that slow fading is better because a signal fluctuation will be very less. But there is one case of slow fading. Like suppose this is the threshold signal power. Now if the signal is slowly fluctuating, once it goes down the threshold power, it will take very long time to come up, right? So for this whole time, the whole channel will be non-usable. That will result in outage. Okay. Suppose we have the signals. These input signals are of symbol duration Ts. Now suppose if we have coherence time that is greater than Ts. So what will happen? Can you tell if it would be slow fading or fast fading?
Slow fading.
Correct.
Uh,
What happens is that when Tc is greater than Ts, then at every point the channel is nearly equal. It will fade very slowly, right? So this will be resulting to slow fading channel. On the other hand, if Tc is less than or equal to Ts, we'll see it in the next page. In this case, if coherence time is less, so signal will be fluctuating more, right? So this will give some fast fading scenario. Correct. So all of this can be summarized into three things. How do we calculate coherence time? First thing is that if we are looking for some exact calculation for coherence time, we go to the plot and then we see where the signal is fluctuating till 90%. So we see the 90% correlation and then from there we can take the coherence time. So first thing is from correlation plot. This would be the exact method of counting. The second is Tc equals to 0.423 by Fm. This is the relaxed condition. And the third one is Tc is 9 upon 16 Fm. In the stricter condition. Okay. Then other thing is if Tc is greater than Ts, then it will lead to slow fading scenario. And if Tc is less than equal to Ts, then this will lead to fast fading. Okay. Any doubt up till here?
No, no.
Okay. So if we take slow fading condition, this slow fading condition can happen if suppose a symbol duration is very small. So what I mean to say is that this criteria Tc greater than Ts is very relative. Like suppose we are saying that Ts is very small, we use another type of modulation, then Ts will change. Then again the suppose if it is slow fading for one type of modulation, it can be fast fading for the other type of modulation. This we will see in the questions that will follow. So one condition is that if Ts is very small, then it can go to slow fading condition, or if mobility is very slow. If mobility is slow, then Fm is less. So if Fm is less, Tc will be greater. Similarly, if mobility is faster, what will happen? Fm will increase. If Fm will increase, coherence time will decrease, and this will go to fast fading situation. Okay. So now here we understood about slow fading and fast fading. Better to take some questions and then we will move forward if time permits. So you see this question in the derivation of bandpass signal correlation that I just did right now. Which one of the following assumptions influences the correlation to follow a Bessel function? So, what did he assume about p theta?
It is equal to 1 by 2 pi. That is uniform, I guess.
Yes, this is uniformly distributed in minus pi to pi. Great. Now this one is question from coherence type. So V you have been given as 80 km per hour and FC is 1 gigahertz. Can you tell the coherence type? So we have to first change it into meter per second, right? Then what would be the next step?
So first we have to calculate Fm for coherence time. So
Correct.
V divided by C into Fc.
Fm should be V divided by C into Fc. That gives us. So can you calculate and tell me how much it is coming? I think it will come at around 74 hertz if I'm not wrong.
Yes, ma'am. 74.
Okay. So now how do we calculate the coherence time? Better to use the stricter formula, that is 9 upon 16 into Fm. So how much it is coming? I think it is coming something as 7.6 millisecond.
Yes, ma'am. 7.6.
Okay, we will see this. If the options are wrong, then we will update. Level crossing rate we haven't discussed yet. So maybe move on to the next question. In this question, a wireless system is using QPSK modulation, and the bitrate is given as 1 Mbps. And for this, the coherence time is given as 1 microsecond. And this is asking the channel experienced by mobile user is slow fading or fast fading. So, what it should be, Dishan?
It's one fast fading, I guess, because symbol time is more.
How did you calculate it? How much is the symbol duration? So we know that symbol duration is in TB, right?
Yes, ma'am.
So for QPSK, how many symbols are there? How many bits are there? Sorry,
2 bits, ma'am, at a
two
time.
bits
We
are
are
there. Hmm, correct. And TB is 1 microsecond, right? So TS is 2 into 1 microsecond, that is 2 microsecond. So you're right, TC is less than TS in this case. So what this will be? Slow or fast?
this fast fading.
Fast fading, correct.
TV is how you found that TV is 1 microsecond?
Here bitrate is given as 1 megabit per second.
Okay, so okay, one by
1
okay.
by. Okay, any doubt? This concept we will discuss in next class and we will take up this question again. This one you tell. With the increase in velocity of receiver, what will happen?
The coherence time will decrease in this case. So first is not true. Uh,
Okay, level
so,
crossing rate again I haven't taught yet. So I'm
so,
planning to take that up in next class.
so no, but if coherence time will decrease, then that means fast fading. So level crossing rate will increase. So two is true. Uh,
Hmm.
Average envelope fade duration. So fade fade duration will also decrease. Average fade duration will decrease since it's a fast fading.
Right.
So three will false. Three is false. Coherence bandwidth decrease. Coherence. So
If
if
coherence time is decreasing, then coherence bandwidth
decreasing,
will increase.
so only two is correct,
Only
I
two,
guess.
that is correct.
So can you just go back to that question at QPS?
Yeah, correct. Tell me.
So in this question, the bit rate is 1 Mbps.
Hmm.
So per second, 1 megabits we are transmitting.
Yeah, 1 megabit
So,
per second.
uh,
So what would be the bit duration for one bit?
hmm, for bit it's 1 microsecond. Okay, simple. Okay, ma'am, I got it.
Okay, some more concept we will discuss before we conclude. So till now we have seen the fast fading and the slow fading scenarios. For slow fading, what is happening at receiver? We have y equals to hx plus n. So suppose our x has some symbol duration ts. So till that time of symbol duration, our h is constant. Right. So if we have channel information, can we estimate x from y? We can estimate x from y as h inverse of y. So for slow fading condition, receiver design is easy. Now we take fast fading scenario. In fast fading, the channel will change at some durations. So suppose if we have x with symbol duration ts, suppose channel is changing. Suppose we say that this is t1. For simplicity, we are assuming that channel is changing 2 times only. So for this scenario, what should be the received signal? For the first time duration, h1 would be the channel and x from the duration 0 to t1. Then for the second scenario, x from t1 plus whatever we say delta ts. So this is a pretty much complicated case. For this case, advanced receivers are required. So like fractional space equalizers, or we can sample it at higher rate. These kind of things are required to be done at the receiver. So basically complexity will increase if we take fast fading scenario. So overall wireless communications, we will be dealing with slow fading only. But previously we have discussed one disadvantage of slow fading. If signal goes in outage, it doesn't come till long period of time. So the channel is unavailable for a long time. This is termed as outage. So what I explained was that suppose this is the threshold. If the channel is slow fading, You see, once it goes into outage, it will be in outage for a long period of time. So in this case, coverage will be affected. So coverage is defined as so the power should be greater than this any threshold gamma th. I think we will be discussing more of it later. There is one concept that I would like to discuss, that is the level crossing rate. This one I missed. Okay, this one will be discussed in the next class when we will see Doppler. This question is AFD and LCR stands for. So LCR is level crossing rate and AFD is average wave duration. This question you see, in that where we discussed about signal correlation, we had assumed P theta is uniform between minus pi to pi. But there can be cases when P theta is not uniform. So here P theta is given as 1 upon k plus 1 P theta plus k upon k plus 1 delta theta minus pi by 3. Here theta is 1 upon 2 pi from minus pi to pi. Now it is asking correlation of real part of small scale channel. So HI delta T you have to calculate, and antenna gain is given as 1. So there is a straightforward formula. Can you solve this?
C.
Sorry,
C.
C. I think this is correct. I'm not sure. I'm missing the formula right now. Maybe we will take this up again in the next class. Then number of resolvable multipath for flat feeding channel is
One.
Yeah. What happens in flat fading channel is that we always assume that all the delays are same. So what happens is that uh, when all the delays are same, the channel is like this is some tau. This is suppose H1t. This is H22. This is 3t. So like that. So what happens equivalently is that it is scaled by some factor which is ht, that is equal to summation of n equal to 1 to suppose n hn of t. So in this case, number of resolvable multipath is 1. Now this problem you see, we have 4 transmitter with transmit power is given and carrier frequency is given. Now P1, P2, P3, P4 are the received power and the path loss expression is given. So what do you think should be the order of P1, P2, P3, P4? And please note that when path loss is higher, then received power would be less. What do you think would be the order? So can we say that path loss is directly proportional to carrier frequency from here?
Yes.
Any doubt?
No.
Okay,
No.
okay. So if carrier frequency is greater, then path loss would be greater. So we have FC1 is greater than FC3 is greater than FC2 is greater than FC1, right? So path loss for first case would be greater than path loss for third case. This would be greater than path loss for second case, and this would be greater than path loss for first case. Now, what do you say about received power?
So received power for one is greater.
This is 4. Hmm.
So uh, okay. So received power for 4 will be greater than 2, then 3, and then 1.
Okay. So this leads to option
B.
B. Great. This anyways I will be taking up in the next class. But average fade duration is given by e to the power minus rho square divided by rho fm into 1 upon square root of 2 pi. So can you use this formula and let me know how much is the Doppler frequency? The average fade duration is given as 10 millisecond. So we have 10 to the power minus 2 e to the power minus 1 upon fm square root of 2 pi. Can you calculate?
This is 1 by FM, I guess.
Oh yeah, yeah. Sorry. So FM would be 1 upon square root of 2 pi e into 10 to the power 2. Now how much it would be?
68 hertz.
Yeah, correct. Okay, so it is coming as 68 hertz. So answer is B. Level crossing rate we says 2 pi fm rho e to the power minus rho square. So level crossing rate is average number of times signal crosses the threshold level. There is the formula for level crossing rate. So suppose your Doppler frequency is given as 100 hertz and the threshold level rho is given as 1. So what would be the level crossing rate?
It's 92 crossings per second.
Okay. So the answer is C. Okay, so I think we will conclude this lecture. Remaining topics we will be covering in the next class. So any other doubt other than this?
No, ma'am.
Okay, then I think this is it for today. We'll meet
Thank
next
you,
week
ma'am.
again at the same time. Okay, thank you.